In this video, I'm going to discuss what is called total internal reflection. So this occurs when a light ray goes from a more dense medium to a less dense medium, or a medium with a high indices of refraction to a medium of low indices of refraction. So essentially what happens is when we shine a light ray from the more dense medium, you can see that then that light ray at a small angle is refracted into the new medium, okay? And according to Snell's law, we have the index of refraction times this angle of incidence is equivalent to this indices of refraction times the angle of refraction here, okay? And notice that when we go from a more dense medium to a less dense medium, this refracted angle moves away from, or bends away from the normal, okay? So if we look here, you can see the green ray, and you can see that there's this angle between the green ray. As I increase the angle, this ray then moves down, but you really maintain the same total angle right here. So there's a point at which I will reach, which we call the critical angle, where the refracted ray actually runs parallel to the interface between the two mediums, okay? Beyond that angle, we say that the ray then is totally internally reflected back into the original medium. So, you know, if I were underwater, this picture of this sea turtle shows an example, right? I can't see out of the water from this position because I am beyond the critical angle. When I look, I see everything totally internally reflected, which is why the surface looks like a mirror here. Now, in order to find the critical angle, we can easily calculate this by using this equation. So the sine of the critical angle is equal to the ratio of the second medium over the first medium. Okay. Now I'm going to show you some examples using a simulation from the FET. Okay, so we saw this yesterday, or in the last video when we looked at Snell's law and refraction. So you can see that at this angle, I am going from a more dense medium to a less dense medium. So I have glass up here and I have air down here, which is the same as what we were just looking at. So you can see that as I change the angle, that the refracted ray then moves, and this entire angle stays the same, right? Okay, and notice that even though some light is being refracted, there's also some light that's not transmitting the surface. So this is somewhat of a reflective surface. So there's some light also being reflected, okay? Now, when I go beyond this point right here, is when I get to the point where everything becomes totally internally reflected back into the medium rather than being refracted through the medium. Okay? So let me just quick perform the calculation, and then I can use my simulation here to confirm my answer. Okay? So if I have the equation, remember, is that the sine of the critical angle is going to be equal to the ratio of n2 over n1. Okay, let me zoom in a little bit on that. So I want to know what that critical angle is when that internal reflection will happen. So I just take n2, which would be the second medium. So that is, in the case over here, remember this is air, so it would be 1. And then our glass up here was 1.5. And then if I do inverse sine, it will give me the angle, right? So I just take 1 divided by 1.5, and then, so I get about 42 degrees is the critical angle. Okay, so let me just go ahead and quickly confirm with my simulation. So I have a protractor here, and I'll just set it right there so you can see this is about 42.